All right, so now we know all about orbitals. Let's talk about what these molecules actually look like in 3 dimensions, okay? Now, when we think about how electrons are going to be positioned around an atom, we need to remember a very basic principle of charge, that the same charges will repel each other, okay? Since all electrons are negatively charged, electron pairs repel each other, and they want to get as far away from each other as it's possible. Okay, so valence shell electron pair repulsion, or VSEPR theory, uses this principle to determine the molecular geometry of an atom based on how many bonds and how many lone pairs that atom has. Okay, so to determine the molecular geometry, we need to start with something called the steric number. And this is going to give us a quick prediction. Okay, the steric number is defined as the number of sigma bonds plus the number of lone pairs around an atom. Again, sigma bonds, we're not counting pi bonds. Okay, remember from the last set of slides, I told you that was going to be important to remember when double and triple bonds, which were sigma, which were pi. Sigma bonds only count, okay? All right, so let's look at some examples here. We've got a carbon. The carbon has 4 sigma bonds, no lone pairs, steric number of 4. Nitrogen has 3 sigma bonds, 1 lone pair, also steric number of 4, okay? And then oxygen finally over at the end has 2 lone pairs, 2 sigma bonds, steric number of 4, okay? If the steric number is 4, okay, then the atom is what we say sp3 hybridized. If the steric number is 2, the atom is sp2 hybridized. And if the steric number is 2, the atom is sp hybridized, okay? All right. For any sp3 hybridized atom, the 4 valence electron pairs will form a tetrahedral electron group geometry, okay? Methane has 4 equal bonds, so the bond angles are all equal to each other, as we can see. They're all 109.5 degrees. Now, the bond angles in ammonia are a little bit smaller, and this is because it doesn't actually have 4 bonds. Even though it has a steric number of 4, one of that steric number came from a lone pair. Okay, this lone pair actually repels the other bonds greater than the bonds are able to repel each other. So it forces those bonds a little bit closer to each other than we see with something like methane or carbon with 4 individual bonds. When you look at oxygen having 2 bonds and 2 lone pairs, we can see the bond angle is even smaller. And again, this is the result of the fact that it has 2 lone pairs. Those lone pairs are able to push on those bonds and get a little bit further away than the bonds are able to push and repel each other. Okay, now, again, the hybridization can then be used once we find out what the hybridization is, to find the molecular geometry, okay? The molecular geometry is described for only the atoms bonded to the central atom that we're talking about. It doesn't involve the lone pairs. Electron group geometry, which we just talked about, does involve the lone pairs. We aren't interested in that. We are only going to be focusing on molecular geometry, what the molecule actually looks like, okay? Okay, so how do we know what the molecule actually looks like? All right, well, you can see that by knowing the steric number, we can then get hybridization very quickly, okay? Once we have the hybridization, we can then get the shape based on knowing how many bonds and how many lone pairs contributed to that steric number. Okay, so you will need to be able to know this chart, to know it, and to be able to actually predict the geometry, molecular geometry of an atom. So let's take a minute to look at it. Okay, if we have an atom that has a steric number of 4 and it has no lone pairs, the steric number comes simply from bonds, it will have a tetrahedral geometry. Okay, if we have, like with nitrogen, steric number of 4 but 1 lone pair, it will have a trigonal pyramidal geometry. And if, like our example with oxygen, we have a steric number of 4 but we have 2 lone pairs, we will have a bent molecular geometry. Okay? For a steric number of 3, we have sp2 hybridization. If the atom has 1 lone pair, it will also be this bent configuration. If it has no lone pairs, it will be a trigonal planar conformation. And then finally, when we have an atom with a steric number of 2, it's really simple. sp hybridized and linear. Okay, so let's do an example together. Okay, I have a molecule here, and I'm pointing an arrow to that carbon. What's the steric number of the carbon? What's its hybridization? And what is the molecular geometry about that carbon? All right. So first we're going to do steric number. Okay. Now I see 2 single bonds and 1 double bond. Okay. Single bonds are always sigma bonds. Always. So I've got 2 sigma bonds right there. And then again, I'm remembering from what we talked about with bonding in the last set of slides that a double bond is composed of 1 sigma bond and 1 pi bond. Okay, so there's 1 sigma bond in the double bond between carbon and oxygen. So I have a total of 3 sigma bonds, no lone pairs. So my steric number is 3. Okay, well, if I have a steric number of 3, that means my hybridization is sp2. Okay. Now, what is the molecular geometry of that carbon based on its hybridization? Okay, well, it's got a steric number of 3 and no lone pairs. According to my chart, this makes it trigonal planar.